Introduction of liquid field detectors. Radiation detectors are essential tools in nuclear science, medical imaging, and environmental monitoring. Liquid field detectors are type of radiation detector that utilize liquid as the active medium for detecting ionizing radiation. It primarily used for detecting alpha, beta, and gamma particles. Also, liquid field detectors offers a sensitive and effective method for detecting and quantifying radiation that allows them to detect low levels of ionizing radiation accurately, making them ideal for precise monitoring facilities, laboratories, and industrial monitoring. Next is the significance of liquid scintillation detector. First, it is highly sensitive instrument that well suited for detecting low energy beta radiation. Liquid scintillation detectors have high sensitivity because they can detect very low level of radiation, especially low energy beta emitters that other detector might miss. Also, this high sensitivity comes from their ability to produce a strong and clear signal even when the radiation energy is minimal. The light produced during detection is amplified by highly sensitive photomultiplier tubes, which can detect even small flashes of light generated by weak radiation. The next significant is versatile sample handling that can be used to quantify wide range isotope, including alpha and beta emitters. This includes low energy beta emitters like tritium, medium energy beta emitters like carbon. The ability to detect such a broad spectrum of isotope with high efficiency and accuracy highlight the detector's flexibility and make it suitable for application in environmental monitoring, radiopharmaceutical research, nuclear safety, and biological studies. Lastly, the compatibility with the biological sample. It is essential in medical, biochemical, and ferrochemical research. Also, the liquid scintillation detectors are well suited for biological sample because they can accurately measure the low energy radiation from isotope commonly used in biology. Samples like blood, urine, cell extract, or tissue can be prepared easily without complicated steps. The detectors give reliable and precise results for different sample types, and special mixture can help reduce signal loss caused by certain chemicals in the sample.
Now we go on to explanation about liquid field detector for radiation detection. In radiation detection, it is called liquid scintillation counter. So what is scintillation? Scintillation is one of the three types of radiator detectors. It is the act of giving off light, and for radiation detection, it is the ability of some material, in this case, which is liquid, to scintillate when exposed to radiation that makes them useful as detectors. So how does it work? The liquid scintillator is a solution containing a fluid, which is a substance that emits light when excited, and a solvent. When radiation interacts with the scintillator, it excites the fluid molecules. The excited fluid molecules then return to their ground state, emitting light photons, and that is scintillators. While liquid scintillation counter is a common and important type, there is also another detector, which is gas field detectors. It can also utilize liquids. To be specific, some gas field detectors may employ a liquid as a quenching agent or to increase the density of the detection medium. So now here we move on to application concept for liquid field detectors. Here we have security and environmental monitoring, nuclear physics, research, industrial and medical imaging. More to see in detail exploration situation after this.
Next, the detailed exploration of liquid field detectors. First, liquid field detectors are used in many fields. In nuclear power plants, they monitor radiation levels. Also, in medical imaging, they help in PET scans and gamma cameras. For environmental monitoring, they detect radiation in water and soil. Next, they are also important in homeland security, where they help detect smuggled radioactive materials. And in scientific research, they are used in experiments involving cosmic rays and neutrinos. Next, I will be explaining about the advantages of liquid field detectors. These detectors offer high sensitivity and good energy resolution. Next, they can also identify different types of radiation, and their liquid form makes them flexible in shape and size. Plus, they work well with AI system and can be used in both portable and field setup.
So, we're gonna move on to the examples of real-world implementations. In the medical field, scintillation detectors play a crucial role, especially in imaging technologies like PET and CT scanners. These detectors are commonly used in hospitals and diagnostic imaging centers. The process starts when patients are injected with a small amount of radio trace known as a radioactive substance that emits gamma rays inside the body. Scintillation detectors, often made from crystals like sodium iodide doped with thallium or lutetium or CO2 silicate that detect these gamma rays. The crystal material absorbs the gamma rays and produces tiny flashes of light, a process known as scintillations. These light flashes are then converted into electrical signals by devices called photodetectors such as photomultiplier tubes. Finally, computer systems process these signals to create detailed images of the body's internal organs or tissues. For example of this technology is the PET scan, which is widely used to detect cancer, monitor brain disorders, or assess heart health. CT scanners also sometimes incorporate scintillation detectors to improve image quality. Besides, scintillation detectors are also widely used for environmental radiation monitoring, particularly in nuclear power plants, environmental monitoring stations, and by disaster response teams. Portable scintillation help detect gamma or beta radiation in the environment. This detector works by converting the energy from radioactive particles into flashes of light. The amount and intensity of this light are directly related to the level of radiation present. This technology is essential for detecting radioactive contamination in water, soil, air, or even biological materials. A real-world example of this is the monitoring efforts that took place after the Fukushima nuclear disaster, where scintillation detectors were used extensively to measure radiation levels and ensure public safety. Other than that, scintillation detectors are essential in space missions, where they are installed on satellites and space probes to measure high-energy radiation from outer space. These detectors are capable of capturing cosmic rays, gamma-ray bursts, and other space radiation, providing critical data for understanding the universe. For instance, NASA's Fermi Gamma Ray Space Telescope uses scintillation detectors to study gamma rays coming from distant cosmic sources. This helps scientists explore phenomena such as black holes, neutron stars, and other energetic events occurring in space. Finally, in the oil and gas industry, scintillation detectors are used in a technique called well logging. These detectors are deployed at oil drilling rigs and exploration sites to help analyze underground rock formations. During well logging, scintillation detectors works by lowering boreholes to measure natural gamma radiation emitted by the surrounding rock layers. By analyzing the intensity and patterns of this radiation, geologists can determine the composition of the rocks and identify the presence of oil or gas deposits. For example, companies such as Schlumberger use this technology to optimize drilling operations and improve the efficiency of oil and gas exploration.
On to the potential benefits we can get by using the scintillators detectors for radiation detection. There are 6 benefits that I will mention, which is pulse shape discrimination, known as PSD, fast response time, scalability, wide variety of materials, high detection efficiency, and cost efficiency. Now, I will briefly explain each potential benefit mentioned. First, the pulse shape discrimination, where lots of liquid scintillators have the ability to differentiate different types of radiation by examining the shape of light pulse or the signal shape. Second is fast response time, where the scintillators release high light from nanosecond to microseconds, thus provide a real-time timing and detecting applications such as TOFs or PET system. The third benefit is the scalability, where experiment can be handled more precisely when using liquid field detectors, as it makes it easy to scale up detectors with large volume. It can also be made in variety sizes and shape. Moving on to the next advantage, scintillators detectors is available in variety of material such as organic and inorganic material like plastic and crystal that can be tailored specifically for different applications. Next is high detection efficiency, where some scintillators detectors have high gamma ray stopping power. Lastly is the cost efficiency, where lower cost is needed as liquid is particularly more cheaper compared to solid state material and also much easier to be fabricated. I will now continue with challenges that may occur when using the scintillation detectors. There is also 6 challenges that I will mention and briefly explain each of them. First is the radiation damage, where high exposure of radiation can lead to degraded light yield, and even small trace of contamination on the liquid can have an adverse effect in reducing the overall performance of the detectors, as it can produce noises in the background or absorption of scintillation light. Second is the temperature control, because some of the liquid require a sophisticated cooling system and insulation. Some of the material used are very sensitive with temperature that require thermal stabilization that will overall increase the cost needed and also complexity in using the liquid field detectors. The third challenges that may happen is the absorption of moisture due to the hygroscopic nature of the liquid. Moving on to the next point, which is the maintenance complexity. This is because some unavoidable problems such as leak or contamination might happen, resulting in complex maintenance procedure needed as it requires a shutdown. Next is the limited energy resolution, where some of the scintillators detectors usually has lower energy resolution compared to semiconductor detectors. Lastly, the very expected challenges that may happen when using the scintillators detector is the safety and handling, as liquid is usually toxic and can be dangerous as it is flammable, making it require a very careful containment and handling procedure.
Now let's talk about future development and innovation in liquid field detector for radiation detection. First, researchers are working on improving radiation discrimination. This means making detectors smarter at telling the difference between types of radiation like alpha, beta, gamma or neutron. With this advancement, detectors can be more accurately used in environmental safety and security application. Next, we have integration with smart system. By connecting detectors to IoT, Internet of Things, we can send real-time data to remote monitoring station. This is especially useful in nuclear plants or hazardous area where human presence should be minimized. Artificial intelligence is also playing a big role. AI helps to process complex radiation data and can detect patterns or anomalies faster than manual analysis. It also helps reduce false alarm by learning what's normal and what's not. Another innovation is the development of eco-friendly and less toxic liquid scintillators. This not only helps the environment but also makes the detectors safer to use, especially in field or during accidents. And finally, new energy efficient design are being explored. These detectors will consume less power, making them ideal for long-term use in remote areas. Some may even be powered by solar energy in the future.
In conclusion, liquid field scintillation detectors are an important technology for detecting radiation. They use special liquids such as organic solutions or noble liquids like xenon and argon to produce light when radiation passes through. This light signal helps to identify and measure different types of radiation, including weak or low energy particles. These detectors are known for their high sensitivity and flexible design, making them useful in many areas like medical imaging, environmental safety, and scientific research. Improvements in these detectors have enhanced their performance, making them more reliable and effective for modern radiation detection.